this session, it's going to be going for about an hour, maybe hour and 15, is going to be looking at some alternatives to null hypothesis significance testing using both Bayesian hypothesis testing, but also equivalence tests. This is scary for a lot of people. Looking at this, seeing a result that's 0.06 is very scary. I think nowadays, 0.04 is almost just as scary. When you get that result, people are going to be like, no one's going to believe me. They're going to think I did some questionable research practices to get there. But regardless, this kind of highlights how much our careers and our research and our papers actually rely on essentially an arbitrary number or an arbitrary threshold. P-values are great for what they do, what they're designed to do, but they also have a number of limitations. They can be used to reject a null hypothesis, which is its main purpose, but you can't actually assess the magnitude of an effect when you get a p-value. A lot of people, when they see a p-value, they'll say, oh, it's really small, and they'll assume this means that the effect was really significant, or the effect was really large. Or they'll get a p-value of like 0.9, they'll be like, it was extremely null. But it doesn't work like that. It doesn't actually give you a measure of magnitude. It's only used as a way to actually reject a null hypothesis. And like I mentioned before, it's largely an arbitrary threshold that we have. We've landed on 0.05. Some fields have different conventions, but in the work that we typically do, we're looking at this threshold of 0.05. But by having a threshold, this sort of stuff has actually led to questionable research practices, as people will do things to their data sets or do things with their research practices to actually get across this magical line. And the funny thing is, even if you get a result of 0.06, a result of 0.06 isn't that different than 0.05, yet it still defines what our results are going to be, even though these things are right next to each other. Now, the other thing is that p-values are largely dependent, or they are dependent on sample size. If you collect enough data, you will actually get a smaller and smaller p-value. To give a good example, there was a study that came out a few years ago that was looking, can Facebook manipulate your feelings? This was a very controversial study that came out, not to mention the ethics. But what Facebook did was they manipulated whether you saw a positive or a negative thing in your feed, and to see, did that actually affect what you posted yourself? So can Facebook actually affect how you feel? And then they did this study, because it's Facebook and they have like 1 billion people they can test. They did this study on 600,000 people. And the p-value was tiny. So a lot of people looked at this going, look at this massive effect. But when you actually look at the effect size of 0.02, it was tiny. You have a large enough sample size, you will reach statistical significance, but it means nothing in terms of how large your effect is. So that is one limitation of p-values or using p-values. And so of course a lot of people say, yes, well we can use effect sizes. We can actually couple our p-values with effect sizes, but effect sizes, they're not immediately intuitive. So we have a different range of effect sizes depending on the kind of test that you're doing. And we also have these thresholds that people sort of say, this equals a small, a medium, or a large effect. So looking at Cohen's D, for instance, if you're doing a 2-sample T-test, these are the thresholds that we have. But when you actually look historically, when Jacob Cohen first proposed these thresholds, Jacob Cohen was saying, well, I'm picking a medium effect size because this is the median effect for this area of psychology, and the small effect is in the first quadrant, and the large effect is in the last quadrant, and this represents what constitutes these effects. But basically, he never designed this to be used as a threshold for everyone to use. Jacob Cohen was like, if you have no idea what sort of effects you're anticipating, then you can use this. This is an absolute backup if you have absolutely no idea. Yet what's happening now is that people aren't even considering what constitutes a medium, small, or a large effect in their research, and they're going back to these thresholds, even if it doesn't necessarily represent their research or what they would consider to be a small, medium, or a large effect. one thing that you can do, I was actually curious as to, within my field, what is a small, medium, or a large effect? So what I did was I actually got and collected all the effect sizes from about 200, almost 300 studies. I collected these effect sizes to actually see what is the median effect, what is the 25th percentile, and what is the 75th percentile, to actually get an idea. And Cohen was almost right. When it came to this field, an effect of 0.05 was actually quite close to what Cohen originally suggested. But the small and the large effects are a little bit different. And this technique, I posted the code for this online, and a lot of people have used the code and used this for their own fields. They've also found an effect of 0.05 is actually pretty close to a median, but they've also found that for them, small and large is quite different. So if you want to get a more accurate idea of what constitutes a small, medium, or large effect in your research, then you actually have to look at your literature. Now, a big issue with this is effect sizes tend to be inflated because of publication bias. So take this with a grain of salt, but it gives you a basic idea of what, this is one strategy that you can use to think about what constitutes a small, medium, or large effect. And I'm going to go into some other ways of determining this later on. Now, what about non-significant effects? The way that p-values work, you can only reject or not reject the null hypothesis. That's it. There's no way, you can't make any inferences about what's happening with the null hypothesis. A lot of people look at these things and they think, well, you know, like I mentioned before, oh, we've got an effect of 0.9, therefore it's really non-significant. But that's not the way that it works. There's essentially two conclusions that you can make with a non-significant result. Either it supports a null model or the data was insensitive. There's no way of knowing which of those two it is just by looking at a non-significant p-value, either insensitive data or a non-significant result. But there is a way that you can actually do this. I think there are three reasons. Oh, I've skipped ahead. There are three reasons to include this sort of tool in your toolbox when it comes to actually figuring out, is there evidence for a null hypothesis or is there evidence for a null model? Because right now, 95% of people within biobehavioral sciences don't have this in their toolkits, which is a real shame. Now, the first reason is perhaps you're interested in actually figuring out whether two groups have equivalent effects. This is a paper that we're currently working on, looking at heart rate variability between schizophrenia, bipolar disorder, and healthy controls. And based on our prior research, we would expect that heart rate variability, which is a measure of parasympathetic nervous system activity, would actually be equivalent between bipolar disorder and schizophrenia. Right now, with typical p-value hypothesis testing, all you could say is, well, these groups were not different. We have no way of knowing whether it's because they're actually equivalent or because the data was insensitive. So looking at the schizophrenia and bipolar, yeah, sure, they look pretty similar, but we actually have no way of knowing using our conventional methods whether they are equivalent. So that's one way to have a think about in your own research. Maybe you're interested in actually finding equivalency between groups. It's not always about finding differences. Sometimes we're interested in actually finding equivalency. The second thing is, what is the evidence for looking at evidence for non-significant effects? A lot of people like looking at oxytocin research and they'll say, oh, look, there's non-significant effects. The whole field is done. Let's forget about it and continue on. And there was a paper that came out where somebody opened up their file drawer of studies they didn't actually publish. And this is very commendable. And they opened up the file drawer and they reported 10 studies and they were like, look, this is non-significant. Oxytocin doesn't work. Change your career path. You need to do something completely different. And so what I did was I actually re-looked at this data to go, well, was it a case of these non-significant p-values actually supporting a null model, or was it insensitive data? And by re-looking at this, I found that almost 80% or just over 70% of these non-significant results were actually due to data insensitivity. So perhaps there are studies in your fields where they're saying, well, these things are non-significant, but by using these techniques, you can actually re-look at these studies to figure out, is it because there's low power, or is there genuinely nothing really going on there? So it's really powerful. And the third reason is it actually gives you an opportunity to falsify your hypotheses. This is the scientific model that we generally work under, where you actually think of an hypothesis and you test it. But right now with our system, all you can do is reject a null hypothesis. You can't actually find support for it. in order for us to move forward in our fields, we need an opportunity to actually falsify our hypotheses. Because what's happening now is that people are getting a non-significant result, and then someone else is going, well, the last person was non-significant. The last study was non-significant. But maybe it was due because the design wasn't great or they didn't have enough power. Let's just try again. But by actually having a tool in your toolkit where you can reject the null hypothesis, this is going to make science much more efficient. So what we should be doing when we're designing our studies is we design how we're going to first essentially see if there's support for our alternative hypothesis, but we should also be designing our studies to say how we're going to find support for our null hypothesis. And by using these techniques, you can exactly do that. And you can get to your results of your study, and you can say, we actually found support for our null hypothesis. Currently, we can't do that with our conventional statistics. Now, first thing we're going to be looking at is the Bayes factor, which quantifies relative evidence. This is key. Relative evidence for a null and an alternative hypothesis. And this is really, really handy. Now, when I wrote a primer paper about 2-3 years ago, which a lot of this stuff comes out of. And one thing I was hesitant to do, there are certain grades of evidence with Bayes factor values. And I was very hesitant to include this because one thing we really should be getting away from with p-values is looking at these thresholds. Or same thing with Cohen's d-values is by looking at these thresholds because we mindlessly think about, well, our study was significant because we hit this magic number. So I was hesitant to include this, but some reviewers were very adamant going, I think you should still do this for the very reason that it gives people some sort of basis to work on of what actually constitutes when it comes to the size of your Bayes factor values. And there's a lot of parallels between these numbers and p-values. Essentially, a Bayes factor of 3, which suggests there's 3 times more relative evidence for the alternative hypothesis relative to the null hypothesis, is actually quite similar to a p-value of 0.05. So like I said, I stressed in the paper going, like, please, like, don't use this as a threshold. Here's just a guide. People are still doing it, but it's a good way to actually start thinking about what sort of evidence that you have when it comes to your own paper. Yeah, so these are largely arbitrary, but it's a good sort of reference to think about. But the thing is, it almost doesn't matter because these things work like an odds ratio, they're directly interpretable. So a p-value of 0.05 isn't directly interpretable, but a Bayes factor of 3 says that looking at our data, we actually have 3 times more evidence for the alternative hypothesis relative to the null. And that's extremely intuitive. Or we could say we have 10 times more evidence for the null hypothesis relative to the null. This is great, and this is a great way of thinking and much more intuitive to how we actually think normally. And this shows you, I think this was a study looking at almost 700 p-values and comparing them to their respective Bayes factors, and you can actually see how closely these things align and how closely the Bayes factor of 3 is roughly corresponding to a Bayes factor of 0.03. And yeah, I will be posting these slides online as well if you are interested, particularly in getting the references too. Now, obviously there are a lot of advantages for using Bayes factors in your research, but it hasn't been used that much. And I think the reason is, to date, there's been a lot of poor availability in the software that we use. You can do this in R, but not everyone uses R. SPSS has just introduced this, but it's extremely basic and doesn't give that many options. But now we actually have fantastic software, point-and-click software, that can do this for us. But I mean, I would recommend, if you're getting into this a bit more, to actually learn how to do this in R. But to begin with, you can actually do a lot of really great stuff by using JASP, which is free software both for your Mac and your PC. And the great thing is it's very easy to export your data and your figures as well. And the plots look really nice, much more nicer than your average SPSS figure. Now, one thing, or the sorts of questions we tend to be interested in our fields, there are 3 questions. One, what is the relationship between 2 variables? Are a set of categorical variables interrelated? And do groups differ on some sort of variable? And what are the role of potential covariates? And these are the 3 things that we're going to be looking at today. So as an example, I'm going to be going through this study, which came out a few years ago, which was looking at what is the role of intranasal oxytocin on self-reported spirituality or to your connection to a higher being. Now, oxytocin is thought to actually be involved in human bonding interaction. So the idea was being, well, what if it's actually involved in some sort of spiritual spiritual relationships? So participants were either randomized to receive oxytocin or placebo, and they were asked a simple question: how spiritual do you feel, or how much connection do you feel? And they were looking at the role of oxytocin on spirituality. I have sent around the dataset as a CSV file, so if you have the time, you can import that into JASP, and we can have a look through. Yeah, so that is the question, what people were asked, and they were also asked the same question a week later. So the specific wording was, would you say that spirituality is important for you? And participants responded on a scale from 0 to 7. So very, very straightforward experimental design. To the researchers' credit, they posted their raw data on OSF, so it was easy to actually extract it. And I was curious, and I had to look through, and it gives an opportunity to also recreate their analyses, but also to do stuff for demonstration purposes. So that's the original link for the original data set. So for the data set that we're working with, I removed some relevant variables just for demonstration, and I created a new category in order to actually recreate the results that they got, because that wasn't in the raw data, which is fine. And then yeah, to make it consistent with the original results, I also removed 4 participants, because I couldn't actually replicate the results to begin with. But then when I looked through carefully, I figured out, well, they did a few different things, but it's still all checked out. Okay, so what you want to do is get your data, open the file up in JASP, and like SPSS, you have to actually, it takes a guess as to what sort of data or what sort of category the data is, but sometimes you do need to change it. So in this case, you do need to change this SP1L variable is the main one we're going to be using. This is the main outcome. How spiritual would you describe yourself? That has to be changed. So click on it and then change it to the ruler, so you can actually work with this data set. Usually it does a pretty good guess of figuring out what sort of data you have, but sometimes you have to go through and actually check and change the category of your data there. Okay, so to make a demonstration, let's just say, before looking at our primary research question of whether oxytocin influences spirituality, we want to ask the question, well, what if age is related to spirituality? What if perhaps older people are more likely to identify with this, or perhaps younger people as well? So the first thing that we can do is run a traditional correlation, a Pearson's correlation, and you'll see that the output or the screen looks very similar to SPSS. And then all you need to do is just drag in your 2 variables. Our 2 variables of interest are age and the SP1L. You drag them across, and you can see there's a few different options for how to actually run your statistics, and there's also the options for plots as well. And so this is just going to give you your conventional output, and so you can see that the relationship actually looks pretty flat. There's not that much going on there. Looking at the results, p-value of 0.7, the Pearson's R statistic is quite small, 0.03, and yeah, whitish sort of error bars. But we can't use this to support the null. All we can say is that we failed to reject the null hypothesis, which is what brings us to our Bayesian alternatives. So looking at this, it's either low power or it's either a null effect. So to do this, we're going to be comparing two models. The idea that there's no correlation between spirituality and age, and the hypothesis of the alternative hypothesis in that these 2 things are actually related. So in order to do that, go up to the screen again, click on the regression tab, and then go down to Bayesian correlation pairs, and you're doing exactly the same thing. You're dragging across both age and spirituality, and then in the plot section, you want to select prior and posterior and additional info, because that's going to give you some nice additional info as well, and leave the other stuff as is. So this is the output that it gives you. Now, with this particular analysis, we're actually saying with this analysis that our prior belief of the data is that the likelihood or the effect size between spirituality and age can be anywhere between -1 and 1. So the idea is that all these potential effects are equally plausible. And when you think about it, that's a bit silly. The fact that we would assume that an effect of 1 or -1 has exactly the same probability of an effect of 0, but we're just going to continue for demonstration purposes. And that's the dashed line in the plot here. This dashed line, because it's flat and goes along, actually says we actually have this prior idea, or we have this idea, and we have no idea actually, and we think that these things are equally likely. So if we're going to continue with this analysis, what this test does is it updates, we test how the observed data updates our belief with the posterior distribution, which is the solid line here. And so we can see that at a value of, when there's no relationship, we can see that it's 6.7 times higher with the prior distribution once we actually see our data. So what this is saying is that our null model has the relative evidence for the null model is almost 7 times more than the alternative model. So there's 7 times more relative evidence for the null model compared to the alternative, which is much more informative than looking at this non-significant p-value. So it's almost 7 times more likely under this idea of a null hypothesis. And you'll notice that there's both a BF10 value and a BF01. The one is basically the inverse of the other. So that they essentially mean the same thing. So BF1, the 0 equals the null. So it's basically saying the relative evidence for 0 compared to 1. So null compared to alternative. And BF10 is the relative evidence of alternative compared to null. These things both mean the same. They're just the inverse. But sometimes it's easier to interpret BF01 because you're saying that there's 6.7 times more relative evidence for the null, 0, compared to the alternative, 1. So yeah, it's simply just the inverse. And you can report either or, but I think because we're interested in a null effect here, it may be more intuitive to actually report BF01. And you'll see that you have what they call pizza wheels in these plots, and this gives you a nice visual indication of what the relative evidence is like. The top one's quite revealing because this is basically what typically represents a p-value of 0.05. So looking at that, you can actually see, well, the results that we trumpet in the literature aren't really that convincing when you're actually looking at the relative evidence for the alternative compared to the null. It doesn't seem very, very, very trustworthy. So you have to think, is this really meaningful? But you can see how these things change when you're adjusting your Bayes factor values. You can also change what is reported by changing the Bayes factor value as well. Now, like I mentioned before, it's pretty implausible that there would be, we would have an idea that each value is equally likely. A value of -1, a value of 1, value of 0 when it comes to a relationship is equally likely. What's more realistic is that values around 0 are more likely and values at the ends are less likely. And you can now see if we can adjust our prior by bunching it more around 0, and that's actually more realistic. And in order to do that, you go back into your price, your beta prior width, and you can adjust that. By default, it's 1, which is flat. But if you actually want to make it more realistic, you can adjust it. And quite a common approach is a beta prior width or a stretch prior width of 0.5, which actually gives you a little bit more. It basically, by doing that, you're saying, I have more belief, or my prior belief is that values around 0 are much more likely. Much more likely than values at the thresholds. So you can adjust that as well. Even if we do this, it doesn't really change our results that much anyway. Okay, so not only are we actually getting evidence for a null or alternative within the same number, we're also getting the magnitude of that evidence. So we're killing 2 birds with 1 stone. usually we have to have a p-value plus effect size. Now we kind of have it all in one. We have this idea of relative evidence and how big this relative evidence is. So in this case, 46 more times more likely under a null compared to an alternative. Going back to our sort of thresholds, this would be considered moderate. But then just by looking at those numbers, I think they tell the story. One criticism of Bayes factor analysis is, well, you can just adjust your prior to get whatever result you want. So there are two perspectives here. If you're hypothesis testing, you either pre-register what your prior is going to be. So if you pre-register, we have chosen this prior distribution because we believe that these things are going to bunch around zero, and that's fine. But if you're doing exploratory research, which is also fine, you can actually plot a range of priors to actually say that our results are relatively insensitive to how wide our priors are. And this is an option. In the plot section, you can do a robustness check to actually see how sensitive is my effect across a range of priors. So if you go back to your analysis and click on the robustness check, you'll get this figure, and you can actually see depending on how wide it is. So this one actually demonstrates that regardless of of your prior, it doesn't really matter. But however, in some circumstances with your results, you're actually going to find that your results tend to be quite sensitive to this. So when you're actually writing these up, you have to actually say in your data, well, you know, this is actually quite sensitive and dependent. We're not that sort of clear on what our results are because this seems to be quite dependent on our prior. If you're doing exploratory research, even if you're doing experimental hypothesis-driven research, I would recommend actually doing this robustness check to actually see how sensitive is your result according to your prior distribution. So the primary outcome is whether intranasal oxytocin affects your self-reported spirituality. So we're going to look at that. We're just going to run a very conventional independent samples T-test. You drag your variables across. Your grouping variable is OT condition, oxytocin condition. And then your dependent is your measure of spirituality. Drag it across. Always go for Welch's test. Always do it because you don't have to assume equal variances. And even it basically gives you an equivalent result to students anyway. So always go with Welch's regardless is my recommendation. And by doing that, and you can see with this plot here, is that there's no significant difference between oxytocin and placebo groups. P-value of 0.3 and a Cohen's D of 0.25. So conventionally, that would be a small that would be a small effect. But once again, it comes back to this idea: non-significant p-value. Was this due to a null model, to the support of a null model, or was it simply statistically underpowered? We can run the same thing again. Instead of running a conventional independent samples T-test, you can do a Bayesian independent samples T-test, drag your variables across, keep your Cauchy prior at the default. So this is, I'm going to go into this a little bit more, but this default is at least a good start. And then you can check your plots. Once again, you can do your Bayes factor robustness check as well. And you drag it across, and we can see that there is actually slightly more evidence for the null hypothesis. Despite the fact, the main result for this paper was that there actually was an impact on spirituality, but that only was when you actually were accounted for, when you were accounting for church attendance, I believe. But when you're just looking at these two things without any covariates, there's actually more evidence for a null hypothesis. So for this, the Bayes factor of 0.1, so the comparison of the null compared to the alternative, was 2.4. So there's 2.4, so the null hypothesis was 2.4 times more likely than the alternative in this case. So, I mean, it's not that much evidence either way. You would typically call this anecdotal type evidence. But when you really think about it, like you just got to think about it practically. Like, is that really convincing? 2 times more? So maybe there's something there, maybe not, which is why it's generally termed to be anecdotal. Now, like conventional significance testing, you can also do directional tests. And the great thing about Bayes factor hypothesis testing is that you can actually use your prior information to actually to set more accurate priors. So say you would have your hypothesis, or you would pre-register your hypothesis that I believe the effect is going to go one way. You can actually adjust your prior in that way. And this is what, so notice that there's nothing going on for minus, but you actually believe there's going to be a positive effect. But still, if we do that, it doesn't really change our results that much. But keep that in mind, that you can actually have a directional hypothesis, which, if you have this prior idea, can actually be quite powerful. The other alternative is, well, typically by using the default the default prior distribution, this assumes that our effect centers around 0. But we need to really think about in our research, is that what we really think? Do we really think the effect centers there? If you look at prior research in your area, you might go, well, there seems to be some modest effects. If we look at oxytocin research, the average effect size for oxytocin research, keeping in mind this is probably inflated, is 0.2. So what you can actually do is you can adjust your prior, or you can adjust the center of your prior distribution to 0.28, to 0.28 or to whatever you want to give you a more realistic prior. You can also adjust how tight your distribution is as well. So if you think that large effects are completely implausible, which is probably right for oxytocin research, then you can actually make your prior distribution a lot tighter as well. So you can actually use your prior information to better inform your analysis. But still, by doing this, and there's still slightly more evidence for the alternative hypothesis when you actually take this approach. So previously using the default, there was actually more evidence for the null. When you use what's called an informed prior, by looking at what's in the literature, there's slightly more evidence. But notice they're both within bounds. It went from like sort of just anecdotal evidence for the null to anecdotal evidence for the alternative. So really, there's not that much going on when you think about it, no matter how you actually adjust for your priors. All right, so what we're going to do is recreate the actual reported, like this study got a lot of media. The love drug makes you more spiritual, all that kind of stuff. But for their actual analysis, they did an ANCOVA, which was controlling for religious affiliation. Basically, are you affiliated with some sort of church or religious institution? So we can do the conventional ANCOVA, dependent variable, the fixed factor of your oxytocin condition, and your covariate of religious affiliation, which is this variable here. And we recreate the result that's reported in the paper. P-value of 0.03, that there is actually an effect of oxytocin administration once you account for religious affiliation. Let's see how this goes when you actually do exactly the same thing. Your fixed factor, your random factor, drag it across for your Bayesian ANCOVA. We actually find there's only anecdotal evidence when we actually take the Bayesian perspective. There's just under 2 times more evidence for the alternative hypothesis that oxytocin influences spirituality once you account for religious affiliation. Which, when you look at it, I mean, that's quite consistent with a p-value hovering around 0.05. So it's another perspective of actually looking at how much evidence or relative evidence is there for this particular effect. These low base factors are generally suggestive of insensitive data. And this is actually quite consistent with a lot of the older oxytocin research, which tended to be statistically underpowered. So the fact that this was below 2 or had a base factor that was quite low is just quite consistent with this idea that, well, we're just not powering our studies well enough. And you can also do a repeated measures ANOVA. So basically, there's an alternative for almost any of these common tests. So here they ask people a week later whether there's any differences. You can go through. It's quite straightforward how you actually do your analyses here, comparing this variable is called SP1 W1 week later, and you can do those repeated measures analysis as well. I don't think this is actually reported in the paper, but there wasn't a main effect of time, and you can see the results there, nor was there any interaction. And yeah, just in your own time, you can go through and you can do your Bayesian repeated measures analysis as well. Exactly the same sort of analysis. The table in the output that it gives you is a little bit different, but essentially what it does is it breaks it down into each main effect. So the main effect, so here we can actually see, noticing that it's a BF01, so we're comparing the relative evidence for the null compared to the alternative. We can see for the main effect of time, and you can see this in the plot, that there was which is the second line in the column, there was over 5 times more evidence for the null, which is pretty clear. It looks pretty flat. There was anecdotal evidence for the oxytocin condition, which you can sort of see there because the error bars are quite wide. Then it also combines both main effects into sort of a larger main effect model, which is still gives you more evidence for the alternative, for the null hypothesis, and it also looks at the interaction. So there are ways of specifically breaking down your model to see for all these models compared to the null how much evidence is there. So it's very handy, and we can actually see what's going on there. Now within this perspective, within this analysis, there's this idea that you can't look at an interaction effect separated from main effects. So to actually look at how strong your interaction effect is, you need to compare it to your main effect. So typically what's done is you actually divide your interaction effect with your main effect and do that comparison there. So you don't look at the interaction effect in isolation, you compare it to your main effect. That's how you actually see how strong your interaction is. But regardless, we can still see a base factor of almost 5, suggesting that there's no evidence for an interaction effect, or there's 5 times more relative evidence for no interaction effect compared to the hypothesis that there is an interaction effect. So yeah, that's just a breakdown of the sort of information that you get from this plot. Yeah. All right. So to summarize, you can compare what's happening both with p-values and with base factors. So there was a lot of non-significant results which aren't very informative. Once you combine these non-significant results with their Bayesian alternatives, you can actually get some very, very interesting information there. Like I said, base factors give you this easily interpretable. It's intuitive. It's like an odds ratio. How much proportionally is there more evidence for one hypothesis compared to another hypothesis? It's fantastic. I think for now, it's a risky ploy. People do it, but it's a risky ploy if you are just submitting papers just with base factors. My experience is that many reviewers are not familiar with base factors, and they're going to tell you, just put in the p-values. So what I do with my papers is I present both side by side. And I say this is the p-value and this is the base factor, because it provides complementary information. It's almost always consistent with each other, but it's especially informative once you are dealing with your non-significant p-value. So if you're doing this with your own work, I would actually present both side by side, either reported in text or in a table. And yeah, JASP keeps getting updated with new features when it comes to the analyses and new types of features as well. And their support forums are fantastic. And there's a few tutorial papers out there now on how to do this. I've written a paper, the JASP team have written their own paper as well, both looking at, there's a massive paper. Part 1 is the theory behind Bayesian hypothesis testing. And it's great because previously these were written by mathematicians and they were extremely difficult to understand. These people have written it for humans. And then we also have a more practical Bayesian hypothesis testing using JASP as well. So I can put those resources online. But then you can also walk through the paper which used the same examples which I used as well. But it does have its limits. If you do actually want a bit more flexibility with your Bayes testing, particularly when it comes to linear models, I typically actually use base factor testing for linear models. So you can't really do that within JASP, but you can do that within the Bayes factor package within R, and that's really handy. So I'd recommend looking into that if you are confident with R. Okay, now we are going to jump into equivalence tests. How to use equivalence tests. Like I mentioned before, I think it's good to have a frequentist alternative. A lot of people still, when they see base factors, they're like, well, why are you changing your statistical philosophy in order to do your analyses? With equivalence testing, you can actually still use p-values to look at these null models or to look at equivalency. There's no way of actually supporting an hypothesis that an effect is exactly 0. That's never going to happen, and that's not realistic. But what you can do is that you can reject effects that are large enough to be considered worthwhile. Now, in reality, this can be quite difficult. Looking at sort of clinical research, for example, there are some sort of thresholds where we would say, you know, somebody looking at the HAM-D, if they're reduced by 50%, we would say that is a treatment response. But in other ways, when you're actually giving out these sort of these tests, you can say, well, people who only move sort of 1 or 2 points from their original value, that is what we would consider no treatment effect. And so you can actually use those values for equivalency. You can actually say, okay, we recognize that some people can actually move a little bit, but that certain values are basically indistinguishable, or they're basically meaningless, even if there is. And this is the idea with equivalence testing, is that you actually set, okay, these are the values that we consider to be essentially meaningless. So we're going to use these in our equivalence test. Yeah, you need to specify these upper and lower bounds of what you consider to be a meaningful effect. When you're combining traditional p-value tests with equivalence tests, there are four potential outcomes that you can get. Outcome A is, now to look at this, we have sort of our mean difference of 0, which would mean that there's no effect. And for argument's sake, we've suggested that a mean difference of 0.05 is what we would consider to be a non-interesting effect, for argument's sake here. So with A, this would suggest that the effect is statistically equivalent and not different. It's not different because it actually crosses the 0, but it's also statistically equivalent because the bounds don't cross those equivalence bounds as 0.05. Now, it's important to recognize that the thick lines represent a 90% confidence interval. Because equivalence tests are two one-sided tests, we use a 90% confidence interval. And that's the interval that we're checking. Does that 90% confidence interval cross our equivalence bounds? And for our traditional p-value tests, we're using the 95% confidence interval. Of course, you're free to change what these intervals are, but these are just the conventions. 95% for p-value and 90% for your equivalence test. So for A, because the thick line doesn't cross the bounds, we would say these effects are statistically equivalent. So if we've got this result, we would say group A is not different than group B. Effect B is because the thick line crosses your equivalence bound, we would say, okay, these effects are not equivalent. And because it doesn't cross 0, the 95 thin line doesn't cross 0, we would say it is also significantly different. This is your conventional result. We had a significantly different result between groups, and these weren't equivalent. Number 3 is that these were equivalent, but also statistically different. You tend to get that with large sample sizes. So you can get an enormous sample size and get a significant result. But essentially what you found was, it's kind of like the Facebook study, yeah? So our Facebook study, we got a p-value which suggested differences, but because those differences were essentially meaningless, they were still equivalent. So that's very handy. And then our final one is that the results were not equivalent and not different as well. So these are the 4 potential outcomes that you can get with your equivalence testing. Now, how to set your equivalence bounds. This is tricky. With some research questions, you can actually ask the question, what is a noticeable effect? Thinking from a clinical perspective, what is a noticeable effect when it comes to the clinical change? When it comes to a cognitive test, there is no hard and fast answers, unfortunately. You can use these thresholds. Like I said before, we shouldn't be using these thresholds mindlessly, but if you have no idea and want somewhere to start, you can use these thresholds and actually say, well, we're going to look at a small Cohen's d of a small effect and consider that to be equivalent. You can also just think about resources, and you can think practically. How many people can you actually afford to test? That's another perspective. And you can run equivalence test power analyses in the R package called TOSTER, which I'll point a link to, and you can actually see for the participants that I have, what do I have enough power, or what do I have 80% power or 90% power to set my equivalence bounds to? Quite often you'll find that you actually don't have the power to make really small equivalence bounds. Remembering, for most of our research, we will consider a very small equivalence bound to be essentially meaningless. But what we tend to find in our research, when we're actually looking at power analyses, for some of us at least, is that we only have the power to actually test very wide equivalence bounds, which is fine, but it only means you can reject these large effects. You should still pre-specify and justify what your bounds are going to be. Like I said before, when it comes to setting your prior distribution, think carefully about when you're, ideally, if it's hypothesis testing, we should be pre-registering our results, and we can say that we consider this to be these effects to be the smallest effect size of interest. We consider a Cohen's d of 0.2 to be our smallest effect size of difference because of X, Y, Z. Maybe it's because of resources. Maybe you have some other reason why. But pre-specify this. There is an Excel spreadsheet available that you can do this, but that was when the package first came out. But I'll recommend to do this. You can do this in R as well. It gives you a bit more flexibility, a few more tests, and you can also do these power analyses that I described as well, a bit more flexibility. Or you can do the TOSTER module in JAMOVI. JAMOVI is fantastic because people can actually write additional modules, and Daniel Larkins has converted, the author of the TOSTER package has converted this into a JAMOVI package where you can run, I think there are 4 or 5 different tests when it comes to equivalence testing. So to look, to use our previous data as an example, we can look at the relationship between spirituality and age. And for argument's sake, we've set our equivalence bounds to -3 to 0.3. So that is our smallest effect size of interest. So what we can do is, if we essentially don't care about effects lower than 0.3, and we consider these to be equivalent. So these are the results here. These are our bounds, and they are, remember, to get equivalency, our bounds would be inside, our error bars would be inside these bounds, but it's way outside. So this basically suggests that if we consider, if we don't care about effects sort of in between 0.2 or 0.3 or whatever we specified, then we have equivalent effects. So that gives you the data there, and it gives you a readout of what these effects are going to be. So yeah, so you can play around with that stuff. There's a few different options there when it comes to correlations and T-tests. I'd recommend going through the Daniel Larkins' papers on actually running equivalence tests. It gives you a few great examples, particularly when it comes to considering how to actually set your smallest effect size of interest or your equivalence bounds. This is something I'm thinking about carefully. I'm working with the collaborator on actually figuring out how do we do this, or how do we, not necessarily what these equivalence bounds are for oxytocin research, but using oxytocin research as a thought experiment of how do we actually determine what our equivalence bounds are, which I think is important, particularly when it comes to this idea, like I mentioned before, of theory falsification. How do we actually falsify our theories? So if we can actually get an understanding of what our smallest effect size of interest is, we can do these equivalence tests and reject these small effects. Yeah, so this is an example with T-test, but you can have a look and just try, put in your own data and have a look around, and you can see how sensitive these different equivalence bounds are as well when it comes to your effects. And I've used equivalence testing in papers, and as long as you explain your methods, exactly what you're doing, and that this is essentially just a different type of p value testing, people are very responsive, and I've got a lot of good feedback on using equivalence testing for my research. So we're gonna wrap up. If you do want some more resources, I share a lot of this stuff on Twitter. I've interviewed Daniel Larkins on our podcast talking about this sort of stuff, so you can check that out. And talking about sort of the pros and cons of Bayesian hypothesis testing and p-values, why people hate p-values and why they're still useful. So I would check out these episodes, which are very stats focused. And I also post a lot of this stuff on my YouTube channel. I do live streaming and basically coding live, showing how to actually do these things for equivalence testing, power analysis, for a whole bunch of stuff. So you can do that. I'd also check out the TOSTER R package if you're comfortable with R. to give you a bit more flexibility. And to do Bayes factor stuff, I would also look at the Bayes factor package. So I'll wrap it up. Thank you for your attention.